Alright, and we're live again. Okay. Let's see. So, yeah, we know, you know, more homework. I have to do more homework because that's what happens when you have classes. Alright. So how y'all been? I'm gonna post everything on everywhere again. I think that is the right link. I'm not posting the wrong link, am I? I'm not. All right. And post this on Twitter. I don't know if there's like a way to like get the link immediately, like after you start stream, like immediately before you start streaming, it like generates a link for you, so you don't have to like paste the link everywhere while you're streaming. All right. Okay. All right. So today we're doing Taylor's again. We're doing more Taylor's classical mechanics. We have two problems today, and it's both on the topic of oscillations. So that's gonna be fun. Okay. The first question is over here. Let me just set everything up so we can get ready to solve this problem. Okay. So, the potential energy of two atoms in a molecule can sometimes be approximated by the Morse function, which looks like this. It doesn't really matter what it really means, I don't think so. But basically, what we're really caring about here is just the fact that it's a Morse function. It looks like this. The function looks like this. So, the function looks like this. So what we do is we just take the let's sketch out this function first. In fact, I drew out this function. I drew this function as a thumbnail for this live stream. So let's first sketch out the function for R. And the function actually looks something like what you saw on the thumbnail of the stream. It looks something like this. Hold on. It doesn't really look like that. You can plug it into desmos.com if you want to like see how it actually looks. But this is how it look like. So R is the distance between two atoms. Yeah, this you can plot this in Desmos. How you can plot this entire function. So yeah, as you can see, there's this point down here. There's this point down here that a particle can be in. It's not like down there, as in physically down below something. It's like if something, it's like where the potential energy is. Like this is the potential energy. Like this is the potential energy, and this is the radius away from the center of the atom. Yeah, R is the distance between the two atoms. So basically, if we consider that the system is in a point of equilibrium. No, let's say a system is somewhere. Let's say we have two atoms in this case, and the distance here is going to be something like R. So maybe initially it might look like it's a little far apart. It might look like they're a little far apart. So it corresponds to the point around here. So the potential energy is around here. The consequence here is the fact that they're kind of far apart, which means there are some, I don't really know what's the pulling factor yet. I'm not quite sure about what the pulling factor is, but there's some pulling factor that pulls this thing inwards, basically making the two atoms get attracted to each other all the way to here. All the way till it's over here. Once it gets past over here, which means that the atom is too close together. The atoms are too close together now. The consequence is that my springs made of springs. Yup, they are made of very small springs. And those very small springs are in turn made of very, very small springs. Everything's made of springs. That's the revelation I've learned. Alright. So, the two atoms are too close together. Now the protons are pushing. No, not. Is it the proton? Probably like both, like probably just the electron. I think there's a. It depends on the my spring is made of. No. No. The springs are in fact made of fucking quantum fields and shit. Alright, so if you're too close together, the atoms start to push each other away. So over here, there's going to be a repulsive force, pushing it. So correspondingly, the potential when it's this close together, it might be over here. And when it's this close together, what happens is the atoms try to push each other. So the atom is gonna likely to like go into this pit over here. This pit over here, right here, at this exact point is the point of equilibrium. The point of equilibrium is where there's no net force acting on the particle. And that's what we want to find. This is the equilibrium separation R naught. At which UR is minimum. There it is. There's all. It says it right there. Hey, I'm early to the stream. Welcome to the stream. So, find the equilibrium separator. At equilibrium, right? Let me zoom in. At equilibrium, what do we have? At equilibrium, the net force is 0. So, basically, F equals 0. Now, another thing you have to factor, you have to know is the fact that the force, a conservative force, a force that is that occurs due to potential energy, the force that occurs due to potential energy is equal to the negative gradient of U. In our case, it is equal to the negative partial derivative of U with respect to R. In our case, because it is symmetric. Is spherically symmetric. So we're trying to find this. We're trying to find the negative partial U by partial R. Del U by del R, yeah. And then we have to set it to be equal to 0 to find where the equilibrium point is. Which you may see, which may look a little familiar because we are trying to find the point where the derivative is 0, which is where the point is at the minimum or the maximum, right? That's what the minimum and maximum point have. Local minimum, local maximum has. It's the fact that its derivative is 0 at that point. And we want to find f equals 0. So let's say we're going to say we're going to need 0 equals to negative partial U by partial R evaluated at R equals R naught. And R naught here is going to be the point of equilibrium. And we already know U as given to us by the question. The U is given to us by the question. So let's just evaluate it. So it's going to be the partial derivative of U with respect to R of A e to the R minus R divided by big S minus 1 squared minus 1. And then we evaluate it at R equals R naught. Today's stream is going to be a little shorter than usual. I hope it is, because I didn't plan much. It's only two questions on classical mechanics. It shouldn't be too hard. Okay, for the sake of simplicity, I'm going to expand this whole term. Wait a minute, something's not right. Yeah, something's not right because A is not supposed to be there. A is supposed to be there. Okay. So for the sake of simplicity, what I'm going to do is I'm going to expand this. A is a constant, so I'm going to pull it out right away. And then -1 here is again is a constant, but like you take the derivative of this term and it's going to become 0. So what's left is basically just e to the r minus r over s minus 1 squared. And that is equal to, of course, evaluate at r equals r naught. And that would be equal to what? That would be equal to, let me just expand it, because I can't use chain rule. You know, I'll just use chain rule. If I use chain rule, what we're gonna have is we're gonna have 2 e to the r minus r over s subtracted by 1. And then the derivative of e to the r minus r over s subtracted by 1, but like it doesn't really matter. The subtraction by 1 doesn't really matter. So here we would have -2a. The negative, I can just put it into that bracket. So we're gonna have e to the r minus r over s. And then that's going to be partial derivative of that, which is going to be minus 1 over s, e to the r minus r over s. Yeah, all right. So that's that, and it's going to be equal to 0 if r equals to r naught. So here r equals r naught, r equals to r naught, and it must be equal to 0. And in all of these terms, a is a constant. It can't really be changed by anything. This is also constant, and this term is definitely not 0. You can't exponentiate something and get 0, unless it's like very big. No, it's very negative infinity. So the only term that could possibly be 0 is this term. Therefore, 1 minus e to r minus r naught over s equals 0. Okay, which of course, if I bring it to the other side, we're gonna have 1 equals to e to the r minus r naught divided by s, and we can take the natural log of both sides. Natural log of 1 is 0. Natural log of this term is going to be natural log of the right hand side, so it's going to be the thing in the exponent. So we have this, and therefore we can conclude that at r naught, where the point is equilibrium, r naught equals r. And that is the answer to this problem. To this part, at least. Yeah, find equilibrium separation r naught, at which this guy is minimum. We found it. Yay! Okay. All right. So, any questions so far? Great. All right. So now, let us expand the Taylor series around the point of the point of equilibrium. So, u of x, according to Taylor series expansion, which you may have learned before, is going to be equal to the value of u at r naught. We're expanding. We are doing the Taylor expansion around the point r naught. So plus the Taylor series expansion, the first derivative at R0 multiplied by R minus R0. I'm sorry, I should change this from X to R. So we're just doing some Taylor series approximation here. And of course we're adding it, we add by 1/2 U double prime R naught times R minus R naught squared. And of course this is the Taylor series, you approximate it, you add in the other terms. Okay. So we now have these we now have this Taylor series approximation. Next thing we have to do is we have to make sure that it's we have to make sure we can write it in the form of Hooke's law. You know how springs, you know how the potential energy of spring, right? The potential energy in a spring is 1/2 kx squared. The potential energy of spring is 1/2 kx squared plus some constant. Of course, the potential energy is relative, so like you have to set like a reference point. Most of the time, for spring, they set the reference point to be x equals 0. So they just set c here to be equal to 0. But in reality, you can set c to be anything. So that's what the value of the Ux of spring is, the potential energy stored in a spring. Of course, we can change this. We can change the variable r to variable x. Well, not really here, but like U r naught here doesn't matter. U r naught here doesn't matter. We'll soon realize why. But here, U prime r naught, what is it? U prime r naught is basically the first derivative of U with respect to r, which before this we set to be equal to 0 at r naught. We set to be equal to 0 at r naught because it's at the point of equilibrium. If the particle is in equilibrium, it means that there's no force. The net force acting on it is 0. Therefore, this one is the force term. This term is a negative force, and therefore, because we're at R0, we are at equilibrium point. Therefore, this term is 0. Then, of course, we have this term up here. U double prime R minus R squared. So I'm gonna write this out, and this is gonna become x squared instead. And then let's try and find, wait, hold on, before that, let's write it out that the potential energy at x, at point x, that is the displacement x away from the point of equilibrium, is approximately equal to some constant, which is the potential energy at the point of equilibrium itself, plus 1/2 U double prime R times the displacement away from the equilibrium, which looks exactly the same like a spring. It looks exactly the same like a spring. And that's why I said it looks exactly the same like a spring. This potential energy looks the same as a spring. And that's why I put in the thumbnail and the title of the stream that everything is a fucking spring. Everything is made of springs. Yeah, basically, this is not limited to just this specific U, this specific potential energy. This technically applies for any potential energy that has this little well over here. Of course, if we have like just a curve like this and there's no well like this, there's no point of equilibrium that would oscillate around the same point. But when we have this kind of equilibrium, where we have this sink, I guess there's this well part, then you can model it as a spring, because this is like what is this is the what is known as a stable equilibrium. This was known as the stable equilibrium. So it's the most stable. It's stable because once you move it away from the equilibrium point, it's gonna get pulled back into the equilibrium point, and then it's gonna oscillate around that point. Whereas an unstable equilibrium will look something like this. If you push it, it goes away immediately. There's no force pulling it back in. So that's what a stable equilibrium and unstable equilibrium is. So U double prime, let's we already took the derivative of this guy, right? Yeah. So we had U prime equals to 2a1 minus e to the, okay. U prime equals 2a1 minus e to the big R minus small r over s. Divided by negative 1 over s, and times e to the e to r minus r over s. Okay. Sorry. I'm a little thirsty. I actually haven't had water in a while. I should have brought some water up here. Oh well. Next, we're gonna have to take the second derivative, and we're gonna have to plug in R naught. So let's just do that. We find the second derivative of this function. So we'll have, I'm gonna just distribute R, that R in. So we'll have R minus R over S subtracted by e to the 2r minus r over s. And you take the partial derivative with respect to r. So we'll end up with negative 2a over s, and then in here we're gonna have a negative 1 over s e to the r minus r over s. This one's gonna be plus 1 over s, no, plus 2 over s e to the r 2r minus r over s. 2 here is not supposed to be up there. Yeah. 2 here should be multiplying the whole function. And then we're gonna have and we're gonna end up with this whole thing, which we can just change this into, I can distribute the negative signs. So we'll end up with 2a over s squared times e to the r minus r naught divided by s plus 2e to the r minus r naught 2e divided by s. But we know that r naught is equal to r because that's where the point of equilibrium is. We found this earlier in the like 5 minutes ago. So we plug it in, we're gonna get that this term becomes e to the power of 0, which is 1. This term becomes, sorry, this is supposed to be negative. This term becomes e to the power of 0, which means this becomes negative 2. So we'll end up with 2a over s squared 1 minus 2. And that's actually not that, because I had an extra negative sign because this was the force. Hold on. I'm sorry, there was not supposed to be a negative sign there. Positive, this would be, we're going to put in a negative sign over there, which becomes 1 minus 1 minus 2, so it becomes minus 1. So it's going to become 2a over s squared. Therefore, the point of equilibrium, at the point of equilibrium, you can approximate the potential to be approximately u r naught plus 1/2 2a over s squared x squared. In this case, u at r is going to be equal to 0 minus a. Okay. U at r here is going to be equal to minus a. There's going to be 1/2 2a over s squared x squared. And this is the potential. This is the potential at x near the point of equilibrium. So let's take the first derivative of this, and we're going to see that we're going to have what looks exactly like a spring force. The force is going to be equal to negative partial derivative of u. Of course, it depends on the degree of freedom. Before this, I use derivative by x. Before this, I use derivative by r. In this case, we use derivative by x now. And we're going to get negative 2a over s squared times 1/2 times 2x, which means these 1/2s cancel out and becomes negative 2a over s squared x, which we can pack this entire guy into k, which gives us f equals negative k. Therefore, we can say that this model, this system can be modeled near the point of equilibrium with a spring force. With that spring force, k equals to 2a over s squared. Isn't that cool? Am I the only one who thinks it's kind of cool? I'm the only one who thinks it's kind of cool because I'm the only one on stream right now. There's no one in chat. Alright. Let's see if there's anything else about this question. So yeah, this is the first question. Fairly simple. I think that was not like, I think there's only like half an hour into the stream. Yeah, half an hour into the stream. We already got one question done. We are on. I hope we'll be. I hope this will be a short stream. I hope the next one doesn't really like completely fuck me up. Alright, so next up we have this question. When a car drives along a washboard road, the regular bump causes the wheels to oscillate. I haven't pasted the question here yet. Hold on. Sorry. Okay. When a car drives along a washboard road, the regular bumps cause the wheels to oscillate on the springs. What actually oscillates is each axle assembly comprising of the axle and its two wheels. Find the speed of my car at which this oscillation resonates, given the following information. A. When 4 8-kilogram men climb up into my car, which means there's a... Yeah. The body sinks by a couple of centimeters. Use this to estimate the spring constant K of each of the 4 springs. B. If an axle assembly, axle plus 2 wheels, has total mass 50 kilograms, what is the natural frequency of the assembly oscillating on its 2 springs? And C. If the bump on the road are 80 centimeters apart, at about what speed would these oscillations go into resonance? Oh boy, this actually looks like a pain. Mainly because the shortest stream it could be shortest stream if this one is if I can decode what this one is trying to say. Like, I understand most of the information here. I understand all of the information here, but what I'm struggling to understand a little bit is this statement. The body sinks by a couple of centimeters. The word couple of centimeters here is really difficult because we don't really know how much exactly. And because we don't know how much exactly it sinks by, like, it could be a little difficult to like approximate. Okay, you know what? Let's give it a try. So let's say the normal amount of, well, the car weight normally looks like this. Before that, hold on. When the this is to estimate on each of the 4 springs. Obviously, that means there are 4 springs. Yeah. All right. So what we can say is we can approximate this to be like a little plate. We can approximate that the car is like a little plate, and then of course we have the we have a spring that looks somewhat like a resistor instead. I can't really draw springs without making it look like a resistor. I mean, I could draw it like this, and it's gonna look like an inductor instead. All right. Okay. So let's say by a couple of centimeters, according to the question, a couple of centimeters means d. D is the distance at which it gets pressed by. So initially it's going to look like this. We're going to assume that this whole thing is massless. Well, the whole system right now is in equilibrium. So I'm going to move this over here. I'm going to copy and paste it. And then if we add if we add the mass of 4 people on it, that is, we have the mass of around 4m added to it with gravitational force g. Then the springs are going to contract down a little bit by a small amount. Well, it really depends. The smallness really depends on how much the mass is and the spring constant. But like, we're gonna say that it's down by a small amount. One sec. Okay, it's moved down by a small amount, and that small amount is d. So let's approximate the fucking spring constant. So initially, the point of equilibrium is where we don't really need to say it's a point of equilibrium. It's like let's say over here we have the force of the 4m, the mass of 4 people. Obviously, I'm gonna plug in 80 kilograms later on. The mass of 4 people is being pulled down by the force mg, but the force mg is being cancelled out by the spring force of 4kd. Okay, 4kd, because as you know, the spring force, when you displace it from the original spot, the force of the spring when you displace it from the original spot is going to be if you displace it by d, then the force acting from each spring is going to be kd. Now we have 4 springs, all of which are displaced by 1d. Therefore, it's equivalent to the force of the spring pushing that up by 4kd. Therefore, Therefore, we can set up the equation that we have 4kd equals to mg, just a simple little equation, equals 4mg, apologies. Therefore, we know d. Well, not really. It says a couple of centimeters. We're going to assume that the couple of centimeters means like 2 to 3 centimeters. But we're not going to plug in the numbers yet. We're going to do this symbolically first. But anyway, we can figure out the mass. No, the spring constant, which is going to be equal to mg over k. No, fuck, not mg over d. Mg over d. It's just that. So for A, the answer is the k, the spring constant, is equal to mg over d, which is let's say it's approximately equal to 80 kilograms by, I don't know, 10 meters per second squared. And let's divide it by, let's say 2 centimeters. A couple of centimeters, I say 2 centimeters makes sense. Or 3 would make more sense, but the numbers doesn't work. Let's go for 4 centimeters. So it would be 0.04 meters. Which is going to give us around, the value of around, what's this, 800 divided by 4 over 100, which is going to be equal to 80,000 divided by 4, which is going to be equal to 20,000 newtons per meter. And that's going to be approximately the value of k. And of course, down here depends on what they mean by a couple. So if by couple, cm, according to the question, is approximately, a couple cm is approximately 4 centimeters. We're going to assume that. I'm getting a little hungry, I don't know why. It's not, I had enough food earlier today, and I don't know why I'm getting a little hungry. Anyway, okay. The spring constant k of each of the 4 springs, we found it successfully. If an axle assembly has total mass 50 kilograms, what is the natural frequency of the assembly oscillating on its 2 springs? Okay, is it a good time to admit that I actually don't? Hello, welcome to the stream. Did I read that chat message like 5 minutes late? Please don't tell me that. Anyway, is it a good time now to admit that I don't know how car springs like work? Like exactly. Because according to this question, is framed a little bit confused in a little confusing way. Like I know how cars work thanks to and you're not gonna believe this. I know how cars work, specifically the springs in the car work, from fucking Build a Boat for Treasure in Roblox. Oh, 2 to 3 minutes. Okay, well, not 5, not bad. So like, what I know is just that there's the car like this, right? And then the cars kind of look like this, and I learned this from Build a Boat for Treasure. Then this is the axle, these are the 2 wheels, and like the spring goes up like this. And like when you have the spring like this, right? The car kind of, when the car falls, the car is on top of here, which the car is something like that. Just imagine a car. And when the car falls or something, the force over here, it doesn't get crushed. Like, you know, the force isn't sudden because we have a spring here to like dampen the force, making sure that it doesn't really. You're looking to create mod add-on too about the track, I think. What track? So yeah, what I'm struggling to understand here is what it means by an axle assembly has the total mass of that. What is the natural frequency of the assembly oscillating on its 2 springs? I don't quite get what this means. Like, what do you mean by oscillating on its 2 springs? Because like we have a car, like there's an add-on that's about making a car thing. Oh, I remember Cookie talked about that some time ago. Yeah, I remember now. I remember now. So yeah, so what I'm thinking, I don't really know how it works still. So like this thing just so That is how I understand it works. But like what it means by an axle assembly has total mass of that and has a natural frequency. And what is the natural frequency of the assembly oscillating on its two springs? What do you mean by oscillate on its two springs? Because like, you know, if you, how does it oscillate on its two springs? Like you can't just leave it like that. Because you know you have a car on top of it. Unless you leave the car on top of it and then you just have this. And how is it gonna oscillate on the spring when the spring's on top? Unless what they also mean is we're also flipping it around. Unless what they mean is we're flipping it around and the floor is over here. No. And then this guy just, and then we have the axle just oscillating up and down, up and down, up and down on its own spring like this. I'm gonna assume this is what it means. Because I honestly don't know what else it could possibly mean. So I'm gonna assume that that's what it means. Alright. So simply we can simply model this. Again, it's just a simple little well, you know, its name implies it, a simple harmonic oscillation. A simple harmonic motion. So here we have a big M, separate from the small m from before because we small m for 8 kilogram men. And then we have two springs, both of spring constant K. Okay. I keep seeing my own like avatar blink in the corner of my eyes because like I have my phone to set up like this to read chat and I keep on seeing my own avatar blink in the corner of my eyes. Honestly, I think I should lower the blink frequency. Hold on. Blink chance, can I turn that up? Yeah, that should be good. That should I should be blinking a little less now. Okay. So obviously here we have another force mg and then we also have two forces pushing it up, which is going to be 2kx. So let's write it out. So let's write out the equation of motion. F equals ma, as we all know. F equals ma. In our case, m is going to be mx double dot. X is going to be the displacement from the x is going to be displacement from the not point of equilibrium. X is going to be the displacement from the, what is it? The original point, like when if there's no m, how long will the spring be? Yeah, when you add m, it gets stretched down. You know what? Fuck it. It's x is gonna be the point of equilibrium. So there's gonna be no mg because the spring force already covers that. We're finding the spring force offset from that energy, from that point of equilibrium further. So mx double dot is going to be equal to it's simply just negative 2kx. In our case, because well, you know, we have two springs, and it's just that simple. We now have x double dot plus 2k over big M x equals 0, and then from this we can immediately know that. From simple harmonic oscillation, we know that x is going to be over time is going to be equal to a times sine omega t plus some phase phi, where omega here is equal to square root 2k over big M. Okay, yeah. 2k over big M. And that is the angular frequency, angular velocity of this setup. So obviously the bigger the value of k is, the more it's actually, wait, hold on. K is, wait, one sec. K is gonna be, K has the unit of newtons per, it's gonna be equal to acceleration times that. If you divide it like that, wait, is the unit consistent? Wait, hold on. K is newtons per meter, which is going to be equal to mass per second squared. You divide by mass. Okay, yeah, that is right. All right. So frequency. Therefore, the natural frequency is going to be equal to 2 pi omega divided by 2 pi, because it's going to be frequency is how often it goes up and down. Angular velocity is how fast it goes from 1 to, well, from 0 to 1. And because one turn is equal to 2 pi radians, angular velocity is going to be, must be faster, must be higher. The value of angular velocity must be higher than the value of frequency, because you have to run around 2 pi radians before you get one rotation. All right, so that's angular velocity, which is going to be equal to 1 over 2 pi times the square root of 2k over big M, which we can calculate immediately by just plugging in the numbers. Give me a sec. Let me just get Desmos open. And then we just plug in 1 over 2 pi times the square root of 2k. So it's going to be that divided by the mass of 50 kilograms, which is going to be approximately 4.5. It's going to be approximately 4.5 hertz. Okay, and then, well, this is actually kind of simple. Wait, so if the bumps on the roads are 20 centimeters apart, at about what speed would those oscillations, would these oscillations go into resonance? I think this is part C. This is part C, okay. This bit is part B. Well, that's kind of simple, because to get resonance, assume that resonance force you have to act force, you have to like act, the force has to be acting on, force acting on uh 4.5 times per second. That's how you get the resonance frequency, because this is the resonance resonance frequency of the axle, right? Imagine a swing. If it swings round and round, and then you get the natural frequency of the swing. You just let it go, it's gonna swing. It's like a pendulum that goes on and on and on and on forever. So that's how so that's pendulum. And then let's say you start to push the pendulum. So if you're standing over here, right, and you push the pendulum when it's over here, give it a boost, and then it comes over here, and it comes back, and then you start giving it a boost over here, and it goes back up, and after you push here, you just let it go, and when it comes back in here, you push it further. So overall, it gets more and more energy, and so this is going to end up being what's known as a resonance. Basically, you're pushing the pendulum at approximately equal rate at which the pendulum is coming back and forth, which means it's going to boost the pendulum's amplitude a lot. Now consider a different scenario where the thing is over here, the pendulum is over here, then it swings over here, it comes here, and then you push it, and once it's over here, you push it again, so it's over here, and then it falls back down, and you push it again, which, as you can see here, is you're not pushing it in the in phase, in sync with the pendulum. So what happens here is when you're pushing it, when it's coming back down and you push it, you're dampening it. Instead of boosting it, you're instead dampening the oscillation. Therefore, the consequence is that this is gonna cause a dampened oscillation, and it's gonna kind of just, it's gonna be a little wonky. But the point here is the fact that once you push it like that, it's not gonna oscillate with very big energy, so it doesn't achieve the resonance. So in the same sense here, to achieve the resonance, it's like the bumps on the road are 80 centimeters apart, which means that you have to, which means that every 80 centimeters you get a push. Every 80 centimeters you get a push, which means that you have to make the push occur every you have to make sure the push occurs every 4.5 times. Yeah, you have to make sure the push occurs 4.5 times every second. That way, it's gonna be pushing in sync with the oscillation of your axle, just like in the case with the pendulum, and you pushing the pendulum. The road is you. The road pushing the pendulum. No, the road is you pushing the pendulum, and the pendulum is the axle. So in our case, to get the resonance, the force has to be acting on 4.5 times per second, which means that in 1 second, you reach 4.5 bumps, which means and each bump is 80 centimeters apart. So that means in 1 second you travel. In 1 second you're gonna have to travel by 36 meters. Therefore, the velocity at which you must be traveling is gonna be 36 meters per second. How much is that in? How much would that be in kilometers per hour? Well, that would be 3600 divided by 1000 times 36. Cancel those guys out. So that's going to be around 100. Around 100 plus kilometers per second, which is no, not kilometers per second. No, I'm sorry. Kilometers per hour, which is kind of fast. But it's for the extra thrill, I guess, so that your car would shake more. If that makes sense. Alright, so that's it. This is on the topic of oscillation. Wait, is that really it? Wait, come on. Wait, I streamed for 1 hour? Is this gonna be... it's not even an hour. This is legit the shortest stream. I don't think I have anything else. So like, I think that's all. We solved 2 problems in like an hour today. Which is the stream is pretty fast. Alright, I don't mind. I'm hungry. I'm low-key kind of hungry, so I don't really mind. Alright, well, thank you for watching. This has been a pretty brief stream. And yeah, see you guys next stream or next video if I do somehow manage to upload before I stream next time, which I honestly don't think that's possible, but who knows? Nothing is certain. Alright, so have a great day. Gonna be playing, no, I'm not gonna be playing Silk Song. No, I have to do homework. I have to do more other homework. It's not like question homework, it's more like writing homework. There are like 2 writing homeworks I have to do right after this. So I'm gonna have to take my leave. Hope you guys enjoyed and got some knowledge, I guess. And thank you for watching. Yeah, have a nice day, night, whatever.